Okay, so now in the second part of this one lecture, technically, we're going to start a new topic. So at this point, I'm going to say we have essentially finished with our number theory section. We discussed modular arithmetic, a new form of addition and multiplication using some finite set of integers. We discussed the fundamental theorem of arithmetic, which says that every integer can be written uniquely as a product of primes. We discussed the division algorithm, we discussed the Euclidean algorithm, and we went through GCD and LCM. So this will furnish us a lot of cool examples with which to try to prove things. So that's good. But what we're going to do now is we're going to move on to chapter 5. And the focus of chapter 5 is going to be to learn a new method of proof. We haven't really discussed new methods of proof since the first month of class when we were doing contrapositive and contradiction and things like that. What we're going to introduce is a powerful new method of proof called induction. And induction is used to prove statements that look like this. You want to use induction to prove statements that look like Pn is true for all, say, n in z greater than 0. Or, for instance, maybe for all n greater than 5 or something like that. But in general, induction is used to prove a whole collection of statements that are kind of depending on the positive integers. Okay, so the basic idea is we want to show that these statements Pn are true for all positive integers, and there are kind of two steps. So 2 steps to an induction argument. The first step is to find an appropriate base case. So find an appropriate base case. And then part B is once you have established or find an appropriate base case and prove it. So usually or often it'll be something like P of 1. There's some statement that depends on the integers, and in the case where P is equal to 1, it's easy to prove just by brute force, just in a straightforward fashion. So the first thing is you find a good base case and you prove it. And then the next step is the inductive step. So the next step is to show for all k that the statement P of k implies P of k plus 1 is true. So this step right here is called the basis step, perhaps. Yeah, the basis step. And this case is going to be the inductive hypothesis. So the book has a kind of nice metaphor where they describe the base case as kind of getting onto a ladder, say some infinitely or maybe even just finitely high ladder. The base case is step onto the ladder, prove the bottom rung of the ladder, and then showing the inductive hypothesis is like showing that if you can grab onto the rung k of the ladder, then you know how to grab onto the rung k plus 1 of the ladder. So if you know how to get onto the ladder and you know how to move one rung up, then there should be no rung on the ladder that you can't climb to. That's kind of the metaphor that I think is kind of nice for understanding the structure of this argument. So if you prove these two steps, then this is sufficient to show Pn for all n where n is greater than 1. Maybe if I wanted to write this out in terms of a formal argument, I would write out if I have the statement P of 1, and if I have the statement for all k, P of k implies P of k plus 1, I can conclude from this argument that for all n greater than 0 in Z, I have P of n. So I've proven some statement for all the positive integers, if I find a statement that depends nicely on the positive integers. Okay, some important remarks. An important remark is that as we go through this proof technique, when we do induction, we don't assume that P of k is true. What we do is we show that if P of k is true, then P of k plus 1 is true. Right? Remember that there are ways for an implication to be true even when the hypothesis of the implication is false. It'll just demand that yeah. So the only time when this whole statement is false is when P of k is true and P of k plus 1 is false. So this is just kind of a reminder on some of these truth tables and what this really signifies as a logical proposition. Okay. What I want to point out as well is that there's a really intimate relationship between induction and the well-ordering principle. So induction and the well-ordering principle. So first, I've already mentioned the well-ordering principle. I mentioned it in some previous lectures when we talked about the Euclidean algorithm, for instance, and also perhaps the division algorithm. So I want to write out explicitly what the well-ordering principle is. So the well-ordering principle is a property of the positive integers, and we take it as an axiom. So that is, in our current version of set theory and in our current naive set theory way of working with the integers, we are going to take this as a hypothesis. Whenever we work with the integers, a hypothesis that we take is that the positive integers can be well ordered. So the well-ordering principle is if, I'll put it this way, any non-trivial, that means not empty or non-empty subset of the positive integers has a least element. Okay, so take any subset of the positive integers that's non-trivial, and by here non-trivial I mean non-empty, and the well-ordering principle says that set has to have some smallest integer. When you take a finite subset of the positive integers, then this is clear. You can take any finite subset and you can pick the smallest one out of those because the positive integers are ordered. For an infinite collection of integers, it's not so clear a priori or naively to say why this should be true. And what we do is we take it as an axiom. So we assume that this is true whenever we're dealing with the integers. What I want to show is that the reason that induction works, the reason why induction is a valid argument, rests on the well-ordering principle. So what I'm going to do is show the following. So suppose that so what I want to show is that this is a valid logical argument. So what I do is I'm going to prove this by contradiction. Suppose P of 1 and for all k, P of k implies P of k plus 1. Assume we have these two things that are known. So I'm assuming these two, and now what I want to show is that this forces P of n to be true for all n greater than 0. And so I'm going to prove by contradiction, assume that there exists an n such that P of n is not true. Assume, for contradiction, that there exists an n in z greater than 1, in this case, such that P of n is false. Then what I do is I say, if there exists some Pn such that, or some n such that Pn is false, then the set A contained inside z greater than 0 such that A in A such that P of A is false. This is some non-trivial set, is not empty. So what I've done is I have assumed for the sake of contradiction that there's some integer such that Pn is false, even though P of 1 and P of k implies P of k plus 1 are both true. Now I have produced some subset of the positive integers. By the well-ordering principle, by well-ordering, the set A must have some least element. And what I'm going to just call it M, say. M. So having a least element means that for all of the integers less than M, the proposition P of those integers are all true. P of M is the first place where, or M is the first place where P of M is a false statement. So then we have P of M minus 1 is true. If P of M minus 1 was false, then M minus 1 would be in the set A, and M minus 1 would be less than M. So if we have assumed that M is the least one, then P of M minus 1 is true. And P of M minus 1 implies P of M, because we know that having this statement for one integer implies it for the next integer. So this is true by modus ponens. P of M is true. And so we have a contradiction. We assumed that we produced a P of M such that P of M was false, and then we also got that P of M is true. So using the well-ordering principle, I'm arguing that induction is a valid logical argument. Okay, so we're going to spend a fair amount of time in this induction chapter, at least a couple lectures. What I'm going to do now is just try to get through some examples so you see what an induction proof looks like. And then, probably in the next lecture, I'll give an overall framework that you should keep in mind when you do inductive proofs. And you'll practice a lot of them on homework, and I'll keep on giving examples. But for the rest of this half lecture, which is 20 more minutes, I want to go through a couple examples. Okay, let's get started. Examples of induction. The first statement that I want to prove is the following. Show that the sum of the first n integers is equal to n times n plus 1 over 2. So show 1 plus 2 plus 3 plus all the way up to n is equal to n times n plus 1 divided by 2. So I'm asserting something about sums of integers. The first thing that I need to do is I need to find an appropriate base case. So basically, this is a whole sequence of propositions. The first proposition being 1 is equal to 1 times 2 over 2. Let me just write down a couple of the propositions, right? P of 1, the first proposition, asserts that 1 is equal to 1 times 1 plus 1 over 2. And this is true. The second proposition is that 2 is equal to 2 times 2 plus 1, or sorry, 1 plus 2 is equal to 2 times 2 plus 1 over 2. Well, this side is 3, and this side is also 3, so this one is also true. The third proposition in this chain of propositions is that 1 plus 2 plus 3, which is 6, is equal to 3 times 3 plus 1 over 2. But this is 3 times 4 over 2, which is also equal to 6. So these are the first couple propositions. And what I'm trying to show is that if I take any arbitrary integer n, like 15 million, then the sum from 1 plus 2 plus 3 plus 4 all the way up to 15 million is equal to 15 million times 15 million plus 1 divided by 2. And I'm not just trying to show it for that one, I'm trying to show it for any arbitrary integer. Okay, how do I do this? First I need to manage my boards. Okay. Sorry. So I'm still trying to use induction on this problem. The first statement, or the base statement, seems to be that first one, right? If I want to show something for all integers, a natural base case, or a place to start, is just with P of 1. So the base case, so proof by induction. First, I need to verify that the base case is true. So base case, verify that P of 1 is true. And indeed, P of 1 is the assertion that 1 is equal to 1 times 1 plus 1 over 2. And this is true. So P of 1 is a true statement. I have checked the base case. The next thing that I want to do is I want to prove the inductive hypothesis. So another thing to point out is that the base case should be something very concrete in terms of your problem. I'm literally plugging in some number and checking that some equation is on the nose satisfied. No symbols flying around. I'm just checking that 1 is equal to 1 in this case. But the inductive hypothesis is going to involve symbols because I need to prove something for all k. So I need to work in the appropriate generality. So let me write out what the statement P of k is. P of k is the following statement. 1 plus 2 plus 3 plus 4 all the way up to k is equal to k times k plus 1 divided by 2. What I want to show is that if I assume P of k to be true, then P of k plus 1 is true. So I want to show that if P of k is true, then P of k plus 1 is true. Now, here is a kind of dangerous step, and I don't mean it's a dangerous step, but I mean the following. At this point, one is tempted to write down precisely what the P of k statement is. The P of k statement is 1 plus 2 plus k plus 1 is equal to k plus 1 times k plus 2 all divided by 2. And it's fine to write down the P of k plus 1 statement. That's what we want to show is true. But there's a common error, which is writing down the P k plus 1 statement, writing down that equality, and then using that in your proof. But you can't use that 1 plus 2 all the way up to k plus 1 is equal to k plus 1 times k plus 2 over 2. So what I want to do is I want to try to do the following. So if I wanted to show P times k plus 1, I want to write out explicitly what one piece of that statement is. So 1 plus 2 plus 3 plus k plus 1, right? This is the left-hand side of the statement pk plus 1. And I want to manipulate this until it's equal to the thing that I want it to be equal to. So the first thing that I'm going to do is I'm going to recognize that somewhere in the statement of pk plus 1 is something involving the statement of pk. In this case, if I'm looking at this sum, and I'm assuming that the sum from 1 up to k is k times k plus 1 over 2, what I'm going to do is I'm going to replace this expression with what it's equal to. So this side is equal to k times k plus 1 over 2 plus k plus 1. I've written out one chunk of pk plus 1, and I've used the inductive hypothesis. So I'm using the fact that I'm assuming that this sum is equal to this, and I'm swapping it out. And now I'm going to proceed with this expression. And I can just work by manipulating this algebraically. Here I can pull out a k plus 1 factor from both pieces of this. So this whole expression is equal to this, which is equal to k plus 1 times k divided by 2 plus 1. This is what I get when I factor out a k plus 1 from both terms. And I want to simplify a little bit. This is equal to k plus 1 times, I get a common denominator, I get k plus 2 over 2, which is equal to, just simplifying one last moment, k plus 1 times k plus 2 over 2. So what I have done here is I have shown that if I assume the inductive hypothesis, if I assume that 1 plus 2 all the way up to k is equal to k times k plus 1 over 2, then this expression, the sum from 1 to k plus 1, is equal to this expression, k plus 1 times k plus 2 over 2. But this expression is precisely p of k plus 1. P of k plus 1 is that the sum 1 plus 2 plus all the way up to k plus 1, or k plus 1, is equal to k plus 1 times k plus 2. Really, it's k plus 1 divided by 2. So what I have shown is that if p of k is true, then I can use that to show p of k plus 1 is true. So since p of k implies p of k plus 1 for all k, we have proven the proposition by induction. P of n for all n. Maybe I'm making some small mistake about terminology. Maybe I should only call this the inductive hypothesis, and then what I'm showing is, using the inductive hypothesis, I'm showing that p of k plus 1 is true. The terminology, okay, I should clarify the terminology. I'll do this in a comment or something like that. But the point is, I have two steps. I have the base case, and then I need to show that for all k, p of k implies p of k plus 1. Okay. Okay, so what I should really say is that the second step in induction is called the inductive step, and this is the inductive hypothesis. The inductive hypothesis is assuming that something is true for p of k. So I'm using the inductive hypothesis here to prove the inductive step, and the inductive step is p of k implies p of k plus 1 for all k. Great. There are some benefits to doing all of this teaching online and pre-recorded. Not many, but okay. So what I want to do next is just do 2 more examples. I want to furnish you with a good chunk of examples so you see how induction works in practice. And then, since there's no meaningful time delay for you between watching this video and watching the next, in the beginning of the next video, I will give kind of a standard recipe that you should follow when doing inductive proofs. I just want to get some examples out. Okay, let's do the following slightly more interesting example. Let's prove for all n greater than 0 that the sum of from k is equal to 1 up to n of k times 2 to the k is equal to n minus 1 times 2 to the n plus 1 plus 2. You can get some really zany and interesting expressions that you're dealing with in this induction. Okay, the first thing that we want to do is write out a couple cases just to get a sense for what's going on. So let me write P of 1. P of 1 is the assertion. Maybe I'll write n greater than or equal to 1. What I'm going to do is I'm going to take n is equal to 1 in this case, and I'm going to say, what is P of 1? P of 1 is telling me from all k from 1 to 1, namely just k is equal to 1, I'm going to have 1 times 2 to the 1. So P of 1 says 1 times 2 to the 1 is equal to, and now n, this number is 1, is equal to 1 minus 1 times 2 to the 1 plus 1 plus 2. Okay? And indeed, this is true. 1 times 2 is equal to 0 plus 2. So this is P1. Let's write out P2. Remember, the left-hand side is a summation where I'm kind of ranging through things. So the first thing that appears on P2 is I need the k equals 1 k, the k equals 1 term. So 1 times 2 to the 1, that's for when k is equal to 1, and then I need when k is equal to 2, plus 2 times 2 to the 2. So this is 2 plus 8, right? 4 times 2 is 8. So 10. And the assertion is that this is equal to 2 minus 1 times 2 to the n plus 1, this being 3 now, plus 2. And indeed, this is also true. 2 plus 8 is equal to 8 plus 2. So this is P2. P3 would have 3 summation terms, and then just one expression like this. Okay, so now after doing this scratch work, I'm going to do the proof. Proof by induction. I'm going to choose a suitable base case. And here, once again, a very suitable and reasonable base case is P of 1. P of 1 is correct for this problem. I need to verify that P of 1 is true. So P of 1 is true since 1 times 2 to the 1 is indeed equal to 1 minus 1, 2 to the 2 plus 2. So P of 1 is true. Now I need to perform the inductive step. Which means I need to show, so show for all k that P of k implies P of k plus 1. K is going to be bad here. For all n, P of n implies P of n plus 1. What I'm going to do is I'm going to show if this is true, then this is true. So the inductive hypothesis is that P of n is true. So let me write down P of n. Well, P of n should be exactly what we have here. P of n says that the sum from k is equal to 1 up to n of k times 2 to the k is equal to n minus 1 times 2 to the n plus 1 plus 2. Now what I want to do is I want to show that P of n plus 1 is true. So I'm going to start off with one side of P of n plus 1. One side of P of n plus 1 is this chunk. K is equal to 1 of up to n plus 1 of k times 2 to the k. Well, this thing is exactly equal to this whole sum, k equals 1 up to n of k times 2 to the k, right? The p of n plus 1 is this junk plus whatever this term is for n plus 1, plus n plus 1 times 2 to the n plus 1. Okay? This big summation is equal to this smaller summation plus the one remaining term. It's exactly the same as what I was doing over here. Okay? What I want to show is that this is equal to the right-hand side of Pn plus 1. So let me just rewrite. The left-hand side of P of n plus 1 is this summation. The summation from k is equal to 1 up to n of k times 2 to the k plus n plus 1 times 2 to the n plus 1. Now what I'm going to use is the inductive hypothesis, which says I'm going to assume that the statement P of n is true. So by the inductive hypothesis, IH, this whole thing is equal to whatever I've got, whatever P of n claims this sum is equal to, namely n minus 1 times 2 to the n plus 1 plus 2. That's this chunk. And then I have to add on n plus 1 times 2 to the n plus 1. So the inductive hypothesis is what allows me to translate from the left-hand side of Pn plus 1 to some different expression that I can work with algebraically. And so now, indeed, what I should do is I should work algebraically. What I see is I have a 2 to the n plus 1 over here and a 2 to the n plus 1 over here. So I could try factoring that out. In other words, I can write this as 2 to the n plus 1 times n minus 1 plus 2 to the n plus 1 times n plus 1, all those in parentheses plus 2. I'm just using commutativity and putting parentheses. That's fine. Then I'm going to pull out the 2 to the n plus 1 from this expression. I can factor it out from both of these terms, leaving the 2 alone. So this is equal to 2 to the n plus 1 times n minus 1 plus n plus 1 plus 2. And with a little more algebraic manipulation, this is equal to 2 to the n plus 1 times 2n plus 2. And I'm nearly there. The last thing that I want to observe is that if I have a 2 to the n plus 1 times a 2 to the n, I can pull out this 2 and get a 2 to the n plus 2. So this whole thing is equal to 2 to the n plus 2 times n plus 2. So let me rewrite what I have gotten using the inductive hypothesis. Using the inductive hypothesis, that is, assuming that P of n is true, what I have shown is that the summation from k is equal to 1 all the way up to n plus 1 of k times 2 to the k. If I trace through, I showed that this was equal to 2 to the n plus 1 plus 1 times n plus 2. But this is precisely the statement p of n plus 1. This is precisely Pn plus 1. Because Pn plus 1 asserts that this sum, the sum from k is equal to 1 all the way up to n plus 1 of k times 2 to the k is equal to 2 to the n plus 1 times n plus 1 minus 1 plus 2. Right? That's exactly the thing that I'm trying to prove. So what we have shown is that P of n implies P of n plus 1 for all n. So by induction, P of n is true for all n. Okay, didn't get through as many examples as I had hoped.